This selective amplifier has very interesting properties. It has to be loaded heavily at this point to get a high Q on the resonance, means a low impedance here, in order to not load the crystal. You can see more about that in the previous videos about this design. Now I am in this video trying to make a noiseless feedback amplifier to place here to see if I can get something that retains the good properties that this amplifier has indicated it would be allow. First I made something like this. These coils are wound on the coil I had before. I think the number of turns was 17 or something like that. And I don't remember exactly the ratios here, and that isn't interesting either, because this didn't turn out well. Well, there is a resistor here also, and of course there is a capacitor here to not destroy instruments or something. The result of this was a lot of flicker noise. Here is the phase noise I observed. At 100 Hz, about -157, and 200 Hz, about -160, 160.5 perhaps. In this graph with state-of-the-art oscillators, those values come here and here, and not very impressive. At close range it's better. Here is 10 Hz, about -145 or so. But statistics is not good enough yet, and this is 14 hours. My equipment isn't good enough to do good measurements below about 15 Hz or so. And 50 Hz here is -154. And those points come here and here. And they all fall on a straight line, like that. And this is quite good. And of course, I expect the steeper third order slope to come at very low frequencies, because Q is about 1.2 million. That is the loaded Q of this design. Now, flicker noise should be reduced if I add more transistors in parallel. But the mechanism is different from my first expectations. I have put 8 of these J310 transistors in parallel. As a result, I had to increase the number of turns here, and I also increased this capacitor quite a lot. I will have to make a new coil, because I don't want the big capacitor. I want to keep the bandwidth maximum here. But the result I get from this is interesting. Here is the close range view with one transistor, and it is 14 hours of collecting data. And here is what I see now with 8 transistors, and this is 40 minutes only. But look at the noise floor here. I haven't reached the noise floor of the unit, because imaginary part and real part are equal in size, or closely equal. But as you can see, the noise is at this level. So at 50 Hz This is minus 162, or even at 30 Hertz, probably minus 160 or so, but it will most certainly go down somewhat more if I wait long enough. 160 at 30 Hertz, that's here. So it is encouraging. Here is the screen after 7 hours with 8 transistors in the second stage of the amplifier. And it's better now than before. I have saved here what I saw with just 1 transistor in the second stage. Now, assuming that each doubling of the number of transistors gives me 3 dB, I should expect 9 decibels, like this. So here is the old data with 1 transistor and 9 decibels. And here is the new. And you can see the scale is the same, nearly, and also the frequency scale. So what I see from here to here, it's about 9 dB. And here I have not collected long enough. So this looks very promising. I will try to tidy up and put more transistors there before I try to optimize anything else. I have reduced the signal level now by 20 decibels. And that is to find the flat noise floor. And it takes only a couple of minutes to see that the level here is minus 152. So that means the flat noise floor is minus 172 dBc per Hertz. The inside is rather ugly now. It isn't optimized for noise. I had expected the flat noise to be somewhere around minus 180 dBc per Hertz. So it's not bad, but it needs an optimization. But before that, I will put more transistors in here and arrange more permanently. The coil, some extra turns, and that was not enough, so I have an extra capacitor here. Well, the schematic diagram is still like this. Here is the curve I have with a new design, new coil and 20 transistors in parallel for the J-FET. The result here is not particularly good. Here is what I observed with a single transistor, and here is now. And the difference is very small, going from here to here, but 3 decibels. And I had 8 decibels before in improvement. And the close range up here, this is the old, and this is what I have now. So there is a slightly different mechanism, I think. Well, maybe not. Anyway, flicker noise has increased in proportion to the number of transistors. And I think I understand the reason. The resonance of the coil on the drain of the first group of transistor is much sharper. And that is because the coupling between the two amplifier stage is weaker. And that is very easy to see because the tuning of the capacitor is very much sharper as compared to before. I have moved these two windings from the edge of the coil at the grounded side to become more like halfway up the coil. And I also increased the number of turns from 1 to 2 here. And this has improved a little bit. This is what I see now. It's 3 hours, 3.5 hours, and that's enough to see the noise. And I set this tool to show. And it's the same everywhere. Well, so this is still flicker noise, and it is 2.5, sorry, it is about 5 dB, and I had 8 decibels before with fewer transistors, so that was better. The noise doesn't come from the number of transistors now, or anymore, I should say. It's another thing, and I will show some interesting aspects of this two amplifier combination. Here is the output impedance, reasonably close to 50 ohms, but 500 pf in series. I can try to eliminate that by putting a suitable inductor in series with the output. But before doing so, I show the effect of tuning. I have a tuning capacitor here, and I can tune it like that, and it has this effect. You can see maximum is here, and you can see how the phase is changing while I'm tuning that capacitor. I have added a series inductor here, 1 microhenry, to reduce the capacitive series impedance I see at this point. And before I have changed to put the big inductor here to allow the toroid to sit without any DC voltage on it, so I can add components here without switching off the power supply, because the power supply is also connected to the thermostat oven which holds the crystals. This has reduced the series capacitance, so it is now looking like a much bigger capacitor. It's a bit noisy, but this is what it looks like. And then when I look at the tuning again, I find a maximum here, and that is with the maximum capacitance on the tuning. I have to add some extra. So I added 33 pf and look for the tuning. It's about here, and now the capacitor is almost at its minimum. But now the output impedance is again capacitive, and it's a larger capacitive reactance. I mean, the series reactance on the output is bigger, and the impedance is also a little bit higher. So the main effect of changing the reactive component on the output is to change the tuning. I'm looking now from the output here to the gates of the transistors here. And here is what I see. The span is 15 megahertz and the reverse signal is fairly strong. It's attenuated by about 20 decibels. But on this point where the coil is tuned, it absorbs some energy from the gate side, so that means that the transfer is a little bit lower. And you can see how that affects the output impedance very strongly. Now, when I look in the data book, gate drain capacitance 1.8 pF, 20 of them is 36 pF. Means I could put an inductor between gate and drain in the order of, let's say, 6.8 pF or 6.8 microhenry or so. I got neutralization here. That is at 8.7 megahertz. But here at 3.7 the output impedance is negative. So this is going towards an oscillator at a very low frequency. I could eliminate that by putting a tuned circuit at the output. But first I will see whether this changes the coupling of the output to the frequency of the resonator. Here is the output impedance, 165 ohms and a lot of series capacitance. Sorry, a small series capacitance, a large series capacitive impedance. So I add an inductor on the output. With the neutralization inductor in place, 6.8 microhenry, I have needed to place 1 microhenry here and 68 ohms here. And this gave me a nice output impedance. The tuning is not much affected anymore. Here is the maximum. And now the output impedance stays the same when I'm doing the tuning. So neutralization of the output FET, that is one thing to do to make this system easier to work with. I have tuned the neutralization inductor, this one, for a perfect attenuation at 10 megahertz by placing some copper foil close to it and bending it for a minimum backwards signal through the amplifier. As a consequence, what I do on the output no longer affects the tuning here of the coil on the drains of the first bunch of transistors. And then I have put some components here at the output to get a good matching to 50 ohms. And here is the frequency response of this amplifier that I have now. I have 100 Hertz for the entire screen. So what I can see at 10 Hertz, it is about 8 decibels attenuation. And 20 Hertz, it is 14 dB. So that's the amount of noise originating in the Wenzel oscillator that will get through when I now use the Wenzel to send through this. And the gain is 10 decibels. It was almost 0 before, so I have much more signal now. Here is what the schematic diagram looks like now. This is the neutralization inductor that I have adjusted for very low coupling this way. And the output transformer, 12 turns and 8 turns, 18 PF, and this 560 ohm resistor makes the impedance 50 ohms at the output, regardless of how I tune this resonator. The thing that has a narrow bandwidth. Now, I don't think these modifications will affect the flicker noise that I'm seeing. I have an idea that flicker noise is probably, I have flicker noise on the phase. Previously, I have only seen that on the amplitude. But now I have phase noise, and what differs here from what I have done previously is the presence of a very sharp resonator here. This capacitor is fairly critical. It was less so when I had just one transistor. When I had those 8 transistors, because I had a much bigger capacitor here then, and the coil was loaded more, I think. Anyway, to investigate whether the flicker noise is due to the varying current through the transistors, I have added 1000 microfarad in parallel to this source resistor, as well as the other source resistor here. The idea is that will give a cutoff frequency of about 30 Hertz for this time constant. So frequencies above 30 Hertz will be have no current feedback in the transistors. So this should increase noise at typically 100 Hertz or so significantly. So the flicker noise curve should be different if the cause is the varying current through the transistors. Indeed, I see much more noise now. Here is some old what I had with just one single FET. And this is what I see now after about 1.5 minutes. So probably those capacitors is what destroyed the phase noise. I will remove one of them. As it turns out, the big capacitors on the sources here and here, they made no difference. So I have removed them and checked other things. And this inductor was critical. It was iron core. I have now put one without any iron. That made an improvement, but still not as good as I had seen before with this same arrangement here. So I also removed this coil, like this. So just loading the drain with the 56 ohm resistor, and also of course the 50 ohm resistor of the load that I'm connecting here. The load will see 50 ohms nearly, accurately enough for the 2-channel correlation system to do accurate measurements of the noise. And here is what I see now after 1.5 hours approximately. And here is the old result with a single transistor. It goes like that. So I'm back at about 5 decibels. I don't want to wait any longer, so I try to read at 50 Hertz. That's where I have the best signal to noise ratio for the phase noise. And here I read -158.5. I have put back the big capacitors on the sources, two of them, so 2000 microfarads here and here. And then I'm collecting noise, sideband noise, phase noise again. The mouse is at -158.5, and that's roughly where I have the noise now. So that big capacitor on sources doesn't make any significant difference. I have now temporarily removed about 5 turns from this coil, like this, and also added about 30 pf fixed capacitor in parallel to this trimmer. The output voltage didn't change significantly, less than a decibel, because of this. This does not work well at all. If I tap very gently on the table, I have these sidebands, vibration on that wire hanging. If I tap gently on the vibration isolation that the box is sitting in, that's what I see. And this affects the measurement of sideband noise, of course. That's phase modulation. And then I can see here the red trace. That's not vibrations, that's some radio signal that comes in, and due to some non-linearity it comes on both sides of the carrier. And to know a little bit more about that, I will look at a wider frequency range. I have partly disconnected that BNC connector that feeds my receiver from the selective amplifier. Means I have pulled the BNC out a little bit. The ground is still connected, but not the center pin. Here we have all the shortwave stations that enter my system. This particular signal comes equally in both channels. If I click on a quiet spot, you can see it is about 15 decibels in the currently selected bandwidth. This one, it comes in channel 1 and it's much stronger there. And another one here, equal in both channels. Oh. And this one also. And if I can look at the strong one here. And now I push the BNC connector to get the signal also. And of course, those radio stations are still present. Some of them, they happen to come close to the overtones of the audio. I have a signal every 700 Hertz, but it's clear, for example, that this one is still the radio signal. It's not my generator. I don't know how to get rid of this. Maybe wait until the stations disappear at night. I have removed those 5 turns permanently. And by the way, here is the neutralization choke. It's about 5 microhenries. The mouse is at 158.5. Already after 21 minutes
this is, I can see that the result now is significantly better than before. The mouse cross is at minus 160 dBc per hertz now. So a couple of fewer turns made things significantly better. I don't know whether that is because of the increased capacitor, I mean the changed LC ratio, or if it is because of a different coupling. I mean the ratio of number of turns on secondary and primary windings on the coil. I will try to find out a little bit more about this. But I also have to look at the wide range noise, how that is affected by the different things that I can do. I have collected correlation averages for now nearly 12 hours, and I can see the noise down to 20 Hertz here. At 10 Hertz here, the correlation, the imaginary part is around here, and it's not far enough, so I cannot say, but the noise is probably below 150 at 10 Hertz. So this looks interesting.
I have evaluated carefully on paper. I'm using this tool, and now it became much sharper. Well, the camera is out of magic. There is the wider frequency range, and then for very large separations I'm looking at the amplitude noise out here. It comes at about minus 172. That's under the assumption that at very large separations what I see is the white noise, which is equal in phase noise and AM noise. Then I plotted those results on a copy of this graph I have with commercially available very good oscillators, and it comes on this line. Here is the frequency response that I have now. The loaded Q is 1.24 million, and the gain through this box is now 0.18 decibels. I made a table of the frequency response like this, and then I have plotted on this diagram the noise that comes from the vent cell, this curve, and then added the loss of the filter, and then I come to this red curve, and it happens to be accurately a straight line. So this line represents the lowest phase noise that I could see if there would be no contribution from the amplifier. And what I did see is about 3 decibels above that, which means that the noise of the amplifier is the same as the noise that goes through the filter. So actually I have here a straight line, because this point is shifted by the noise that comes through the crystal. Now I want to optimize the amplifier. That means current here by this resistor value, and also of course the current in the second group of transistors, the number of turns on the main coil and on the 2 other coils, and possibly some other things could have some effect. And then, of course, to optimize the output, here. Now I'm just loading the drain of the FET with about 25 ohms. So the gain of this last stage is very low. When I increase the load impedance, maybe that will cause a problem. I will see. Anyway, it is very slow to look at what happens by measuring phase noise like I have done up to now. So I have provided a second input, a wideband input like this. This is 30 pf. It happens to be in resonance with 10 microhenry, which means when I change for the other input, this is a high impedance point. I don't change the reactive component that the FETs look into. And with 30 pf and 50 ohms here, I have a 50 ohm match here, and the gain is the same this way or this way on the resonance. And well away from the resonance, the impedance that the source of the FETs see is very high in both these positions of the switch. And here is what I see on the network analyzer for the wideband input. The gain is 0.35 dB. That's 0.2 dB higher than when I'm going through the crystal. And if I look at the wide frequency range, frequency span 5 megahertz, this is what I see. So it looks like I should increase the capacitance a little bit on the big coil. Anyway, now I have a wideband input, so I can do some fast experiments to see the noise of the amplifier. So this should be a more appropriate tuning, but the gain did not change significantly. It varies a little with statistics, as you can see. Input 50 ohms. To study the amplifier in wideband mode, the second input, I'm using interferometry with this setup that you can see here. First, the Wenzel oscillator, and this is a fine stepped attenuator by which I set the power level into the device under test to plus 8 dBm, which is the level that I'm designing for here. So this level is applied plus 8 dBm during these experiments. Then I have a coarse stepped attenuator, and this I can set a large attenuation. And to start with, I will look at the effect of this with this switch in the off position, means there is no signal passing here. So what I have is a straight experiment. The signal goes this way. It's 8 dBm here, minus whatever I'm setting at this point. And then the signal goes into a coupler from where I extract it and amplify and send into the oscilloscope. And the main signal goes through here into an hybrid, followed by low-pass filters and stepped attenuators into the two-channel receiver, which I have here. First, I will verify the coarse attenuator, this one. I set it to 30 decibels, And then I expect to see a 30 decibels loss of signal here, and also at this point, the 2-channel receiver. To do this, I have to set the attenuators here. I set them to 30 decibels because otherwise this receiver would saturate when I have no attenuation here. The oscilloscope shows 2.93 volts, and I verify with the tuning here that I am on the maximum. Something like this. And then I look at the linear screen. Well, I have to wait. And it is 0 on the lower on channel 2 and plus 0.2 on channel 1. Is that visible here? Well, and then I switch in on the coarse attenuator here, 30 decibels, like that. And the oscilloscope, of course, gets a much weaker signal. Point 97, and the linear screen. I remember that old reading, and then I get the new result here. So 29.6, or maybe 29.7 or 8. And here it's 29.7 or so. So it's close to 30 decibels. And now I remember that with the voltage markers on the oscilloscope. This is a 30 decibel lower carrier. Actually, 96 millivolts comes closer. I can compute from that. This ratio gives that, and the power ratio is 931. Gives me 29.69 dB. The difference is from here. Both of them give 29.74 dB. So I can say this attenuator gives me 29.7. Now I have restored the full power level into the interferometer by switching off these attenuators. And then I increased the gain of the 2-channel receiver by removing those 30 decibels in the 2 channels. So now the carrier is suppressed by 29.7 decibels. And I can evaluate what I had before I changed anything now. It says 29.6, should have been 29.5. So that's within 0.1 dB, and that's from using the oscilloscope. Here I'm collecting correlation spectra. Right now I have clicked on the carrier and calibrated the S-meter to show close to 0. And then I click at 10 kilohertz offset here and look for the noise floor. And
I have a wide bandwidth relatively, so I don't have to wait very long. It says minus 136.9 dBc per hertz. And the correlation advantage is 1.82. So, adding those numbers up, I get minus 168.5 dBc per hertz. That is the level of the noise. This is the correlation advantage. And this is the carrier suppression due to the interferometer. And then amplitude noise and phase noise are both 3 decibels below that. Now this is close to the minus 172 I estimated with some modest accuracy from the amplitude noise after having collected for over 10 hours. So this is much quicker and much more accurate. Here is now phase noise connected during 10 minutes. And I can read phase noise all the way down to about 1 hertz here. Probably, reasonably, no. The correlation, the imaginary part goes up rapidly, but 2 hertz is okay. Within 1 dB or so. The amplitude noise comes here, and it's similar. And I can look at a wider frequency range, 0.2 here. I set the X scale there. And here you can see this is the amplitude noise. And if I look for amplitude as well as phase noise, you can see the amplitude noise is flat already, but the phase noise slopes a little bit still. 0.05. So here is AM noise and phase noise, and it goes towards 142, as you can see here. That means 172. That sounds familiar. I can make this table from the screens that I saved on paper. So here are the observed values. They are corrected for the 29.7 dB of the suppressed carrier. The difference from the floor, that is 171.5 according to what I found from the wideband correlation spectra, assuming phase noise equals amplitude noise at wide range. So I say at infinite separation or very large separation, I see minus 171.5. So I take the distance from that in dB, 0 up to 14 dB at 20 Hertz. Convert to linear power scale, saying that the power is a factor of 1 above minus 171.5 and up to a factor of 27. Then I subtract the wide noise, means subtract 1 from the linear, and then I arrive at 1 kilohertz. The noise added from flicker is only half the noise that comes from the white noise, the noise floor. Go back to decibels and add back the minus 171.5. So here is the flicker noise. And then I plot that on my diagram. It's the blue points. Here is the corrected, and here is the observed value. And the observed goes asymptotically down to minus 171.5,
while this is on a perfect straight line all the way up to about 10 Hertz. And here it deviates, and at 2 Hertz it deviates strongly. I don't know the reason. It could be an artifact of my system, means the time constant of the PLL loop, for example, or some other problem that I could attack at some other time, but there is no reason now because I cannot use it anyway when measuring oscillators because of the high noise of my test system, which doesn't come into account here when measuring in an interferometer. Anyway, this agrees well, so I can use this method to try to push this line further down and this other line for the very large separations also a little bit further down. Best would be to observe flicker noise somewhere around 50 to 100 Hertz, because there I could make quicker measurements by using larger bandwidth. But as it turns out, there are big spur problems around 50 Hertz, and they are better visible here. So this is the region most suited for evaluation. I can use it now because of the high resolution, but to save time I would like to run with a smaller FFT, and then I cannot distinguish these lines from the noise that forms the curve that I'm interested in. So before proceeding, I will try to do something about the spurs. Note that the slope of this green line here, that is 1 over f. I have only fitted it to the points vertically. The ruler is at -172, so that's where the flat noise is. To evaluate the position of the line, I like to have it set something like 10 decibels above the flat noise to easily get the flicker noise as a separate observation as compared to the wide noise that I get from some other measurement. 10 decibels, that is at 70 Hertz or 50 Hertz or so. That's why I say I want to measure flicker noise in the region around 50 Hertz. Here is the close range waterfall. I tap gently on the table, just like this. And you see these strong signals come up. So that is a mechanical resonance, and there are several resonances. This is best clear from the spectrum. So this could be difficult, but I could probably find at least some a little bit better. I can switch off the oscilloscope. Do that here. And this spur went away, and that was not vibrations, it was something else. But the sensitivity to knocking on the table is still there. And then of course I have 50 Hertz and 100 Hertz offset, that's the mains and its overtone. But they are narrow band and I know where they are. So I will have to look for the mechanical resonance here and also find a way to be able to run the oscilloscope while measuring. I touch things gently with this Teflon tube, like that. Nothing happens. Well, Here I could see something. Once again. It doesn't seem to be the main resonance, it's another one. Oh, but here, I don't know if you can see that. It is two series connected small capacitors that form a perfect mechanical resonator at some 50 Hertz approximately. I will fix that. I have fixed the obvious mechanical resonances that I found. I have not made any electrical change and tuning has not changed. The oscilloscope is running and I don't see the spur from it, at least not much. If I knock on the table now fairly heavily, like that, I see these resonances, but not those ones that were so strong before. If I bang it really hard. So this is a resonance somewhere, and I don't know where it is. Well, anyway, this is very much better than before, so I will look at the normal way of measuring phase noise. This is what I see after 2 minutes. And I don't need this high resolution anymore. And I don't need to measure below 10 Hertz or so. So I can set parameters to make this run much faster. So I can run something like this. If I clear now the correlation, like that, and then you can see the imaginary part goes down. I want it maybe 10 decibels down. And that's now 15 seconds. Maybe 1 minute. Not more. Well, 30 seconds is enough to get an accurate reading at from 40 Hertz to 200 Hertz or so. So this can be used to quickly see the changes that occur when I change something inside the amplifier. I changed the number of turns on the gate coil here from 5 to 0. Means I grounded the gate directly without coupling to this coil. And here is what I see. I just collected now 20 averages, 15 seconds. The previous measurement with 5 turns was like this. Note that the scale here hasn't changed. So this is a fairly large loss of performance. Now it's here, something like that. Well, what I could see at the wide range at 10 kilohertz, I had lost half a decibel. But here I have lost maybe it's 4 decibels. So I will go the other direction. And I will continue to make little changes, and I will not make a recording of that. I will come back when I have some more final results on these things. I should add that when I removed the gate winding, I had to decrease this capacitance significantly by 20 pf or something. So I could instead have reduced the number of turns on the main coil. And I don't know I mean, to get back a big capacitor to make the influence of varying capacitance in the transistors smaller. I don't know these things from the theoretical point of view, so I have to do it purely empirically.